In this video, we're going to introduce another important class of functions, namely the polynomials. Polynomials are, on the one hand, rather simple kinds of functions to define. Indeed, they're defined using only the operations of addition and multiplication. On the other hand, polynomials are rich enough and interesting enough that one can spend a lot of time studying them, and they have applications in all sorts of different disciplines. Recall that a polynomial expression is arrived at by adding together powers of x, each of which may be multiplied by a constant. So a very simple example of a polynomial expression is the expression 2 times x. Something a bit more complicated, like a quadratic expression, x squared minus 5x plus 4, also counts as a polynomial, as does the expression x raised to the power 100 minus 7. Or a more complicated expression such as this one. Once again, a polynomial expression is arrived at by taking various powers of x, multiplying each one of them by a constant, and then adding them together. And notice that the power of each additive term is constrained to be a non-negative integer. Our goal, however, is not to speak only of expressions, but to speak of functions. And so we will say that a polynomial, or polynomial function, is a function that can take the form shown here. Notice that everything to the right of the equal sign is nothing other than the general form of a polynomial expression. And so a polynomial function is one that can be put into the form f of x equals some polynomial expression. Note that each of the so-called coefficients, a sub n minus 1, and so on, going all the way down to a sub 1 and a sub 0, are just real number constants. Each instance of x is raised to a certain non-negative integer power, and we've gone ahead and arranged the terms here so that the highest power of x appears first, the second largest power of x appears second, and so on and so forth, going all the way down to the power x to the 1 and the constant term, which is really just x to the 0 times a0. In order to help us understand polynomials, we're going to first investigate a simpler class of functions, which are sometimes known as power functions. These functions are the additive terms in a polynomial, and they always take the form of some constant a times a variable x raised to some power n. That power n can technically be any real number, but for the time being, we're just going to focus on when n is a non-negative integer. These functions really are the building blocks of polynomials, and they're also known as monomials because they consist of a single term, a single additive term. Let's take a look at the graphs of some of the basic power functions. What we're going to do here is assume that the coefficient in front of x is just equal to 1 for the sake of simplicity, and try to understand what the function f of x equals x raised to some power looks like. Here we see the graph of x to the power 0, which is just the constant function 1. And unsurprisingly, its graph is a horizontal line at height 1. It never changes. Increasing the exponent to 1, we now get a linear function whose slope is 1 and which passes through the origin. The power function x raised to the power 2, or x squared, has a more interesting graph, which looks as follows. This graph is an example of a parabola. The power function x to the power 3, or x cubed, has a graph that looks like this. And notice how this time this graph is negative for negative values of x and positive for positive values of x. This is the graph of the power function x to the power 4. This graph certainly resembles a parabola, but be careful, it is not a parabola like the graph of x squared. The key difference is that in between -1 and 1, this graph hugs the x-axis more closely. And the reason for that is if you take a number in between -1 and 1 and raise it to a higher power, it will be closer to 0. On the other hand, for values of x that are greater than 1, or less than -1, notice how this function grows more rapidly. And that's because if you take a real number x, which is greater than 1 or less than -1, and raise it to a large even power, you will get a very large output. That's the key difference between the function x to the 4 and the function x squared. Now let's take a look at one more power function. This is the power function x raised to the power 5. The graph of x to the power 5 resembles the graph of x cubed, but it also is not the same. And the key difference here, once again, is that in between -1 and 1, the graph of x to the power 5 hugs the x-axis more closely than the graph of x cubed. And for values of x that are greater than 1 or less than -1, the function x to the power 5 is more extreme. It grows more rapidly than x cubed. That's the key difference here as well. So for powers n that are greater than 1, we begin to recognize a pattern here. In fact, there's a clear separation between the case when that power is even and when that power is odd. For even powers of n greater than 1, x to the n has kind of a cup shape, like the parabola x squared. On the other hand, for odd values of n greater than 1, the graph of x to the n has what we might call a saddle shape, like the function x cubed. Something else we might notice is that as the input x gets very large and goes to positive or negative infinity, the output of a power function with an even exponent will always go to the same infinity. On the other hand, if the power function has an odd power, then the values of the function will go to different infinities as x goes to positive or to negative infinity. What these last two observations are getting at is the so-called asymptotic behavior of a function. Fancy sounding word, but all it's driving at is the question, what happens to a function, f of x, as the input x gets large? Or in other words, what is the long-range behavior of a function like? So to be a bit more formal in our notation, we might ask, as x approaches, or as x goes to infinity, what value, if anything, does the function f of x go to or approach? Likewise, if x goes to negative infinity, then does the function f of x approach some particular value? If we can answer these questions, then we can describe the asymptotic behavior of the function f. Shown here is the graph of the power function, or monomial, minus 3x squared. Let's ask about its asymptotic behavior. Well, one thing that the graph makes quite clear is that if the input x is a large positive number, then the output of our function will be a large negative number. And likewise, if the input of the function is a large negative number, the output will also be a large negative number. The reason for this is actually quite straightforward if we consider the formula that defines our function. If we take a number x, which is very large, square it, and then multiply the result by -3, we'll obtain a negative number that is very large. And we can express this a bit more formally by saying that as x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x also goes to negative infinity. Shown here is a different power function, namely 1/2 x cubed. Let's think about its asymptotic behavior as well. This time, if the input x is a very large positive number, then notice how the output of the function will also be a very large positive number. But if x is a very large negative number, then the output of the function will be a very large negative number as well. The reason for this is that if you take a large number and cube it, then it will retain its sign, right? So if that number is positive and you cube it, then it will still be positive, but very large. And multiplying it by 1/2 doesn't really change that. On the other hand, if you take a large negative number and cube it, then the result will still be negative, and multiplying it by positive 1/2 will keep it negative. We would therefore say of this function that as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x goes to negative infinity as well. So the asymptotic behavior of a power function really depends on just two things: the exponent of the power function, n, and the number or coefficient that's sitting in front of the x to the n term. It turns out that these two pieces of information are enough to determine the asymptotic behavior of a general polynomial. So let's go ahead and put the formula for a general polynomial back on the screen and create a definition and single out a couple things. If the coefficient a sub n in front of the x to the n term is not equal to 0, then we say that the degree of the polynomial is equal to n. And we say that the leading coefficient of the function f is a sub n. So the degree of a polynomial is just the highest power of x that appears in it. And the leading coefficient is the number that's being multiplied by that highest power of x to the n. Although general polynomials are more difficult to analyze than power functions, their asymptotic behavior is not. The reason is that all of the lower order terms, the one for which the power of x is less than the degree of the polynomial, become negligible as x goes to positive or negative infinity. That is to say, they just don't grow nearly as rapidly as that x to the n term, and can therefore be discarded in considering the asymptotic behavior. Indeed, the asymptotic behavior of a general polynomial is determined solely by the leading term, and therefore we can analyze it using the same tools that we use to analyze the asymptotic behavior of a power function. So let's try to describe the asymptotic behavior of the polynomial minus 1/6 times x to the fourth plus x cubed minus 4x plus 5. The key idea is that we only have to focus our attention on the highest power of x, in other words, the term that determines the degree of the polynomial, and the leading coefficient, which in this case is minus 1/6. The asymptotic behavior of the polynomial will be the same as the asymptotic behavior of the power function inside our yellow box. Namely, as x goes to positive or to negative infinity, the polynomial will go to negative infinity. In fact, here's the graph of the polynomial f. Its graph doesn't much look like the graph of a power function. However, it is true that the asymptotic behavior is determined by the leading term. Indeed, as x gets very large in either the positive or in the negative direction, notice how the values of the polynomial become dominated by that leading term and will go to negative infinity.